So due to this increasing object mass flux in the hydrogen, there's a substantial increase in condensation, in turn increasing the cloud liquid as a source of accretion of cloud liquid by precipitation or collection of a cloud droplet by precipitation or raindrop. So eventually there's a substantial increase in the collection of cloud liquid or droplet by precipitation or raindrop. So as you can see from this simplified precipitation budget equation for high aerosol run minus control run, this increase in accretion offset the substantial decrease in autoconversion. I explained the decrease in autoconversion at the first slide, right? So there is a microphysical change, and the microphysical change expresses autoconversion. But this autoconversion is offset by the increase in the accretion. Okay? So finally, resulting in very small difference in total precipitation amount despite the huge difference in aerosol concentration. So we can raise the question, why are there this larger condensation and object mass fluxes for this very small difference in total precipitation amount between the runs? Okay, so let me see these figures. These figures are obtained 10 hours 45 minutes after the beginning of a simulation, corresponding to the mature stage of convective development when maximum precipitation occurs. Here, blue contours represent evaporation rate. Red dashed contours represent condensation rate. Obviously, the arrows represent wind flow field. So here, I mean condensation entities. Okay, the condensation entities actually represent the cloud cells. Okay, cloud is formed by updraft producing condensation. Okay, so that's why these condensation entities can represent the cloud cells. So in the high aerosol, there are 5 cloud cells developing, while there's only 1 cell developing in the control run. So these more numerous cloud cells are associated with more numerous updraft cores, leading to larger domain average updraft and condensation, finally resulting in very small difference in total precipitation amount between the runs. Here I want to put emphasis on the fact that there are, anyway, distinct differences in cloud field properties or cloud system organization represented by cloud cell population. So why there's this type of very substantial difference, huge difference in cloud field properties? To answer this question, these fields are obtained again 10 hours 50 minutes after the beginning of simulation, corresponding to the initial stage of convective development. You see, I mean, there's no difference in cloud system organization around the initial stage of cloud development, but there's a much larger evaporative cooling occurring in the high aerosol run, okay, creating this stronger and more extensive cold pool in the high aerosol run. Due to delayed autoconversion, there's more cloud liquid in the cloud, so that there is more transportation of cloud liquid to the unsaturated areas, causing this higher evaporation in the high aerosol run. Okay, so leading to this stronger cold pool, making stronger temperature contrast with the surrounding warm air, okay, or generating the stronger gust front between cold pool and the surrounding warm air. In other words, there's a larger MAPE, mean available potential energy, developing in the high aerosol run between cold pool and the surrounding warm air. So due to much larger evaporative cooling, there's a more negative buoyancy developing in the high aerosol run, inducing stronger downdraft in the high aerosol run. Okay, and the downdraft reaches surface, and then downdraft spread out toward the warm air more strongly and more extensively in the high aerosol run to uplift the surrounding warm air later on more strongly and more extensively. Okay, so then actually there's to satisfy mass conservation, later on there's development of divergence from warm air to cold air, completing circulation pattern around the gust front, stronger in the high aerosol run. Anyways, this stronger uplifting of the surrounding warm air finally leads to more numerous cells in the high aerosol. About 20 minutes later, there's only 1 cell developing in the controller, but in the high aerosol there are 4 cells developing. And with the 10-minute time progress associated with the weaker gust front, this remains 1 cell, okay, in the controller. But for the identical time progress associated with stronger gust front, in the high aerozone, this cell develops into two cells. This cell also develops into two cells. Finally, at the mature stage of convective development, there are 5 cells developing in the high aerozone, while there's only 1 cell developing in the control run, demonstrating or reconfirming the substantial differences in the cloud system organization and its evolution between the runs. All right, let me look at the precipitation frequency distribution. Okay, so for the precipitation which rate above 27 millimeters per hour, there's presence of precipitation in the high aerozone. But and also, but there's no precipitation in the control run for this precipitation rate range. Also, for the precipitation which rate below 5 millimeters per hour, there's a large frequency in the high aerozone. With this frequency distribution, high aerozone shows about 9% larger cumulative precipitation, as mentioned. The interesting thing is that the average cloud size is smaller in the high aerozone than in the control run, as you can see from these numbers in the parentheses. Okay. Then to see the effect of aerosol-induced increase in evap cooling on the frequency distribution, high aerozone is repeated with reduced evap cooling to the level of evap cooling in the control run. In this repeated run, in contrast to the situation between high aerozone and control run, for the precipitation which rate below 5 millimeters per hour, there's a smaller frequency than that in the control run. This is mainly due to the decrease in the number of small clouds whose size is smaller than the average cloud size in the control, which is 7.1 kilometer. Note that these small clouds mainly produce precipitation, okay, with rate smaller than 5 millimeters per hour. So with this change, the cumulative precipitation in this repeated run becomes smaller than that in the control run. Also, decrease in the number of small clouds shift cloud size to the level larger than that in the control run. So the slightly larger cumulative precipitation and the smaller cloud size in the high aerozone than in the control run associated with the effect of aerosol and cloud system organization are very strongly controlled by aerosol effect on evap cooling and gust front. Also, recent study by Rosenfeld et al. Has shown that the aerosol-induced increase in freezing can affect convection substantially. So motivated by this, to see the effect of aerosol-induced increase in freezing on the frequency distribution, high aerosol run is repeated again with reduced freezing to the level of freezing in the control. In this repeated run, interestingly, there's no precipitation for the precipitation which rate above 27 millimeters per hour. Okay, in contrast to the situation in the high aerosol run. So intermittent heavy precipitation here, kind of associated with the extreme weather event, kind of considering that the y-axis is in the lower scale, is strongly controlled by aerosol effect on freezing. However, cumulative precipitation in this repeated run is still larger than that in the control run, and so cloud size is still smaller than that in the control run. So slightly larger cumulative precipitation and smaller cloud size in the higher than in the control run are not that sensitive to the freezing, although freezing has a substantial impact on extreme weather event here. All right, so let me summarize this part of the presentation. So for 2-day theta simulations, a tenfold aerosol perturbation has a very small effect on total precipitation amount. However, we find more significant changes to cloud system organization and frequency distribution of rain rates. High aerosol simulations have a larger number of small clouds producing lower rain rates through development of more evaporation and a stronger gust front. It is also found that aerosol-induced increase in freezing causes intermittent heavy precipitation. However, its impact on cloud system organization is negligible. Finally, we want to stress the importance of considering aerosol precipitation interaction in cloud system, okay, not a single cloud, over sufficiently long period of time so that we can see the full effect of aerosol on cloud system organization. All right, let me move to the next part. If we have any questions, don't hesitate to give me them. So yeah, I'm ready to answer some questions. So, all right, so the second part is about aerosol-induced heating of the atmosphere and its effect on warm cumulus cloud associated with the effect of aerosol acting as a radiation observant, okay, on the horizontal temperature gradient. Okay, it's well known that the warm cumulus clouds are strongly linked to climate. So to understand the climate change, definitely we need to study warm cumulus cloud, like a trade wind, trade cumulus. Okay, so also it is very well known that the black carbon aerosol can hit and stabilize the atmosphere, suppressing the subsequently developing clouds, so-called aerosol semi-direct effect. Based on this, we can raise this possibility that aerosol pollution or aerosol perturbation occupying only a small portion of domain of interest to us can generate horizontal gradient of the radiative heating and the temperature, which can generate circulations affecting the convection and the feedbacks therein. So motivated by this, this part of presentation aims to understand mechanisms through which black carbon aerosols affect circulations and convection in warm cumulus clouds. For this understanding, numerical simulations are performed by using warp model coupled to two-moment microphysics and injective aerosol module. Using this model, a case of a warm cumulus cloud over tropical region, specifically over the Amazon, is simulated over three-dimensional domain, 30 km by 30 km horizontally, vertically 5 km. Simulations here last 9 hours. Grid spacing is horizontally 100 meter, vertically 50 meter, kind of a ADS model setup. Okay. Only for the prescription of initial aerosol concentration and the analysis of the result, the horizontal domain is divided into two areas as shown in this diagram, area A and area B. In area B, aerosol concentration is fixed at 50 per cubic centimeter. But based on observation in area A, there is a jump in aerosol concentration from 50 to 5,000 per cubic centimeter. In a layer between 1.2 kilometer and 2.4 kilometer. This black carbon aerosol, not entirely. 91% ammonium sulfate, 9% black carbon. So the single scattering albedo is around 0.9 at the wavelengths, solar wavelengths of around 0.47 micrometer. 47, yeah, in the visible light, range. So this is this kind of perturbation is caused by biomass burning over the Amazon. Yeah. So this, you see, I mean, there's a gradient of aerosol concentration between area A and the area B. So the aerosol perturbation does not cover all domain. It just covers portion of the domain. Kind of, I mean, very, similar to the case with biomass burning. So over the Amazon or over the Southeast Asia. So this kind of a gradient is existing now. So with this gradient, first the simulation is performed, aerosol referred to as aerosol gradient, and then aerosol gradient is repeated with the area B. Area B. This is low aerosol concentration extended to all domain, all parts of domain. So in this repeated run, just in all parts of domain, just the aerosol concentration is around just 50 per cubic centimeter throughout most of the boundary layer. Okay, this repeated run is referred to as no aerosol gradient, and the comparison between these two runs will identify the role played by gradient of the radiation observing aerosol. Of the radiation observing aerosol in circulations, convection, and feedbacks therein. All right, so let me first show you the simulated time series of a domain average liquid path, LWP. All right, so in no aerosol gradient, as you can see from comparison between thick lines, there's almost negligible difference in the evolution of LWP between area A and area B. However, in aerosol gradient, there's about 2 times larger LWP developing in area A than in area B. Okay. These numbers are the average LWP over the whole domain, including both area A and area B, and over the whole simulation period. You see, these numbers show very small difference between the runs. So this gives us very important indication that the aerosol perturbation in area A in aerosol gradient tends to redistribute cloud amount represented by LWP spatially as compared to the LWP spatial distribution in no aerosol gradient. Okay, so what is causing this type of redistribution? To answer this question, I obtained vertical distributions of time and domain averaged radiative heating here. So you see, aerosol gradient in area A, there's much larger radiative heating developing, right? This is mainly due to larger aerosol concentration. And in no aerosol gradient, but there's a negligible difference in rate of heating. This is mainly due to the negligible difference in aerosol concentration between the areas. So there's a negligible difference in rate of heating, the stability, convective intensity, okay, leading to negligible difference in L2P between area A and area B. But in aerosol gradient, it is much larger rate of heating, according to traditional understanding of aerosol semi-direct effect, should lead to much larger stability and weaker convective intensity. And this should lead to much smaller L2P in area A than in area B. But results here are totally contrary to this reasoning based on traditional understanding of aerosol semi-direct effect, since area A has a much larger LWP than in area B. So what is the cause of that? That is caused by the circulation pattern developing, as you can see from this wind vector field for aerosol gradient, average over the whole simulation period and over the x direction domain. Okay, so you see, there's a more larger rate of heating in area A, right? So the buoyancy is higher in area A. So the air in area A tends to rise up. Okay, then to satisfy mass conservation, there's a conversion from area B to area A. This again induces downdraft in area B, leading to development of divergence from warm air to cold air, or from area A to area B. Completing this type of circulation pattern relative to the center of the domain, and these updraft in area A and downdraft in area B lead to 2 times larger LWP in area A than in area B. All right, so the gradient of aerosol absorption of solar radiation generate horizontal temperature gradient and circulations. These circulations not only affect clouds in area A, directly affected by aerosol pollution, but also affect clouds over area B, not directly affected by air pollution, far away from the pollution source. This indicates that the effect of aerosol pollution can be teleconnected to clouds far away from the pollution source. So this again indicates that we need to consider a much larger domain than domain directly affected by pollution. So for example, if there's a huge pollution in the Busan area, that pollution can generate this type of circulations to affect the clouds maybe in Kim area. So that's kind of possibility should be considered for more comprehensive understanding of aerosol cloud interactions. All right, so let me move to the overall discussion for today's presentation. So aerosol effectively modifies horizontal temperature gradient environment. With this modification, when aerosol acts as a CCN, there's intensification of gust front in thick convective clouds. With this modification, when aerosol acts as a radiation absorbent, there's a circulation generated, extending beyond the areas directly affected by aerosol pollution. So understanding of aerosol cloud interactions should not be limited to in-cloud interactions, but extended to interactions between clouds and their environment. It is also found that aerosol effect on interactions between clouds and environment do not affect total cloud mass and the precipitation amount significantly, but affect their spatial temporal distribution substantially. Also, on a global scale and over a sufficiently long period of time, evaporation should balance out precipitation at the surface. So aerosol-induced change in total precipitation amount, even at global scale, should not be that large. So aerosol effect on cloud mass and the precipitation should be viewed as a problem of redistribution of precipitation and the cloud mass, closely linked to cloud system organization. And the cloud system organization is strongly dependent on the spatial temporal scale of circulations. So considering this strong linkage between cloud system organization and distributions, and the strong dependence of cloud system organization on the spatial temporal scale of circulation in which cloud systems embed, we can raise this possibility that aerosol effect on redistribution are likely to be different in large-scale circulations, such as Hadley and monsoon circulations, as compared to redistribution simulated here with the mesoscale circulations, mesoscale domain. Also, my recent study has shown that the aerosol perturbed system reach a stable equilibrium state, which is similar to unperturbed systems over a long period of time. Let's look at this time series of LWP from simulations for warm cumulus cloud over tropical ocean. Observed actual LICO campaign. There are two simulations, control run, clean simulation, low aerosol case, and high aerosol polluted simulation, high aerosol case. Comparison between the runs starts around 6 hours, since first 6 hours are considered to be spin-up period. So between 6 hours and 14 hours, high aerosol shows a larger LWP, okay? But between 14 and 20 hours, control run shows LWP. But eventually, after 20 hours, LWP reaches some equilibrium state. Very similar between the runs, control run and high aerosol run. But the cloud system organization represented by LWP spatial distribution is very different even after 20 hours, although cloud system organization reaches its own equilibrium state for each of the runs. Okay, these simulations are performed with a mesoscale domain, again considering strong linkage between cloud system organization and redistributions, and the strong dependence of the cloud system organization on the spatial temporal scale of circulations. We can raise this question for a much longer period and large-scale domain covering the large-scale circulations, like monsoon circulations, what equilibrium in the redistribution and associated environment which will be reached? I think the answer to this question is very important because this equilibrium state will have substantial impact on future distribution of cold air, warm air, flooding, and drought, having substantial implications for us socially and economically. So let me wrap up this part of presentation with the following statement associated with this question. So according to the results shown here, once the equilibrium state of the cloud is perturbed by aerosol perturbation, cloud system tried to reach new equilibrium state, but it tried to reach new equilibrium state not that deviant from its original equilibrium state in terms of cloud system's domain average properties, such as domain average cumulative precipitation. To reach a new equilibrium state, the cloud system develops circulations as a process of dispersing the heat energy perturbation caused by aerosol perturbation. This is similar to the situation when we throw a stone at a pond. So to disperse the pressure perturbation from the stone, pond develops gravity wave or ripples. Here, pond corresponds to cloud system, stone corresponds to aerosol perturbation, pressure perturbation, heat energy perturbation, ripples, circulations. So through the development of circulation as shown in this presentation, there are changes in cloud system organization, leading to changes in precipitation, spatial temporal distribution. Also, the dispersion of the heat energy perturbation redistribute the temperature. Okay, so these redistributions, we can say that these redistributions of temperature, precipitation distribution, precipitation amount are byproduct of a system's effort to reach a new equilibrium state, which is to minimize the change in its domain properties. So anyway, so as I mentioned, that these redistributions have substantial implications for us socially and economically. So, I mean, instead of just talking about global average change in temperature and the precipitation, by providing more detailed information on these redistributions, society can gear up for future climate change in a more practical way.